Okay, welcome to the second or third session today. We will start with Matan Mussel, now at NIH. A while ago he was for a few years a postdoc with me in Dortmund, and he will talk about the electrical and chemical and mechanical aspects of acoustic pulses in the membrane. Thank you, Mark.
Hi. I have a poster at the back of the room where I describe my current research, but today I will describe a work which I have conducted a year ago when I was still a postdoc with Matthias Schneider. And I would like to take this opportunity and thank Matthias and his students for organizing this wonderful workshop. So I'm truly excited to be here. And in this talk, I will describe a theoretical model of acoustic pulses in soft materials, and with particular focus on lipid membranes. And the reason I became interested in this topic is because acoustic pulses and lipid membranes share many similar properties with action potentials. And this idea is related to a conjecture which was proposed by Dr. Konrad Kaufmann in 1989, which action potentials may better be described as an acoustic phenomenon. And Professor Thomas Heimburg and Professor Matthias Schneider have contributed many theoretical arguments and much experimental evidence, which kind of shows many positive signs towards this conjecture. And what I did here is simply following their giant footsteps with this model. Since my main interest is action potentials, let me start by briefly reviewing the key experimental observations of action potentials. The most famous characteristic of action potentials is their sigmoidal response to excitation amplitude. In the biological nomenclature, this is called an all-or-none behavior or a threshold response. Action potentials annihilate upon collision, and you can excite action potentials by many different types of stimulations. Injecting electric currents, exciting them mechanically or locally changing the temperature, pH, other chemical agents, or using light at different wavelengths. I would also like to go over the scales of the phenomenon. So here's a graph which shows the propagation velocity of action potentials in different types of cells. And as Matthias mentioned, they vary significantly between cells, 6 orders of magnitude. Slowest action potentials propagate at a velocity of 1 millimeter per second, and the most rapid action potentials propagate at a velocity of 100 meters per second. The time duration of a pulse also vary by 5 orders of magnitude. The shortest action potentials last a millisecond, while the longest one lasts tens of seconds. And there's also the voltage scale of both the resting potential and the pulse amplitude, and these, in all action potentials in all cells, are of the order of 10 to 100 millivolts, plus or minus. So I'm showing you all of these key experimental observations, and I will show in this talk how acoustic pulses and lipids share the same properties, and we will discuss how these scales arise. I would like to say one more thing about action potentials. When I started to read the classical textbooks on action potentials, my impression was that these are pulses which exist only in specialized cells, only in neurons. No, not only neurons, because I also read that you find action potentials in muscle cells, but I was later surprised to learn that action potentials actually exist in many other types of cells, including epithelial cells, enteroendocrine cells, pancreas beta cells, and glia cells. Action potentials were also observed in fibroblasts, osteoblasts, macrophages, taste buds, salivary glands, and lung cancer cells. And also in oocytes, and in many other types of cells whose name I simply don't know, in corals, plants, fungi, and single-cell organisms. So my point is from this slide that this seems to be a rather general phenomenon in the living cells. I'm going to switch it. So. Right. And now to a completely different topic which has no relation to action potentials. I would like to discuss acoustic pulses in soft materials. And in principle, every material has acoustic pulses inside. Gases, liquids, solids, and lipids are no different. Matthias described how for the last 10 years he has been investigating acoustic pulses in lipids. systems. And one important property for our discussion is the fact that you can find many liquid or crystalline phases in lipids separated by sharp transitions. And this is an example of a static phase diagram measurement or a projection of a small part of it in a lipid monolayer. So what you see is a slow measurement of the pressure, the lateral pressure on the y-axis as a function of density, that's the x-axis going to the left, and temperature, which is represented by the different black lines. So every point in this graph represents a state of the system, a macroscopic state of the system. And we have one phase over here and another phase over here, and they are separated by sharp transitions. They're almost horizontal lines. In the monolayer nomenclature, this is called the liquid expanded phase, and this is called the liquid condensed phase. But you can find very similar graphs in many different materials. For example, in water, in the gas-liquid transitions, where the boiling temperature. And the first order approximation of such a transition is the van der Waals model. The van der Waals, without getting into the molecular constituents, simply make two assumptions, that the molecules of the material, whatever the material is, have a slight attraction toward one another, but they cannot penetrate one another. So there's an exclusion of volume. And these two properties give these kind of nonlinear graphs, where we have one phase and another one, and below the blue region is the coexistence of phases, or the region of phase transition. Now, the pulses I'm interested in, which again, it follows from the ideas of Dr. Kaufman, Professor Heimburg, and Professor Schneider, are acoustic pulses which reversibly traverse a phase transition. And I would like to give a simple example of what I mean by reversibly traverse a phase transition. So think about water slightly above the boiling temperature, say at 101 degrees Celsius. So the water or gas everywhere. And now we excite an acoustic pulse. And locally, near the excitation point, so the system is somewhere here in the gas phase, and now we slightly increase the density. So just near the excitation point, the state of the system moves a bit to the left, because density increases a bit. And since density increases a bit, pressure also goes up. Pressure increases, so it also goes up a bit on the state diagram. And as a result, also temperature rises a little bit. This is the classical description of an acoustic pulse. But now imagine that we use such a large amplitude of excitation that the density increases so much that this local region liquefies. So everywhere the water is gas, temperature is 101 degrees Celsius, but just near our excitation point, the state shifted to the liquid phase if we're talking about water. Right? Now energy is transferred to neighboring molecules, then this region expands, density goes down, pressure goes down, temperature goes down, and the system goes back to the gas phase. And the question I'm asking is, what are the properties of such acoustic pulses which reversibly traverse a phase transition and propagate this reversible change of phase? All right. I would like to give one more motivation why I think this question is interesting and relevant for our discussion, and it is this paper. It is a mathematical paper called Dynamic Phase Transitions in a van der Waals Fluid. It was written by Professor Marshall Slamrod from the Department of Mathematics at the University of Wisconsin. And this paper deals with nothing related to this present interest except this one sentence somewhere towards the end of the introduction. And it reads as follows. Surprisingly, the equations governing the problem given here and the generalized Fitts-Nagumo equations are similar. Now, the Fitts-Nagumo equations is a simplified version of the Hodgkin-Huxley model. So the Fitts-Nagumo equations basically give rise to pulses which have the properties of action potentials. They have the shapes which look like action potentials, they have the all-or-none behavior, annihilate upon collision, etc., etc. And when I read this sentence, my imagine kind of jumped and I thought, wow, if these fluid dynamic equations near phase transition has some kind of mathematical similarity to the Fitts-Nagumo equations, maybe, just maybe, the behavior of these acoustic pulses near transition will show similarities to action potentials. So I went on to solve these equations and study the solutions. And now we start to model a soft system. How do we do that? I don't want to get into the molecular description. I want to stay on the macroscopic level. And as Matthias described, I'm going to start from conservation laws. So I'm going to assume that the molecules of the material do not appear or disappear out of nowhere. This is the conservation of mass. And if we locally apply forces on the system, then we have local changes in momentum. And similarly, if we locally apply work on the system, there are changes in energy, and energy can transfer into heat, and heat can diffuse from low to high temperatures. These are the starting points of a hydrodynamic description. Every hydrodynamic form, from predicting the weather to blood flow, is based on these assumptions. And I've adopted the equations given by the paper I just showed, but these are almost the general equations you can find anywhere, from low-Reynolds dynamic flows and up to predicting the weather. And these equations describe the dynamic relation between 5 variables of the system. This is how I'm describing the system. I have the density field, or the specific area, it's just the same, it's the inverse, the velocity field, energy field, pressure field, and temperature fields. All are basically equations of space and time. So we have 5 variables and 3 equations. We need 2 more equations to close the system. And usually in hydrodynamics, the researchers use an ideal gas relation. And since I'm interested in a phase transition problem, I'm going to use the van der Waals constitutive relation as a first order approximation of the transitions that we identify in liquids, in lipids, or in liquids. It can be quite general. So it can be a model for, a pure lipid membrane, but also a material which is composed of lipids and proteins embedded within. So we're talking about a soft material, and there are several parameters of the material, like the viscosity and the heat capacity and the thermal conductivity. Right. Okay, so now let me start and show you some solutions. So, we describe the material, we think about this kind of 2-dimensional planar geometry, and we excite planar waves, so the equation, the problem becomes a 1-dimensional problem in space. And this is, of course, not my solution. These are experimental results conducted by Shami Shrivastava and Matthias Schneider. And these 2 graphs represent a measurement of the density of a lipid monolayer as a function of time at a specific point. And the lower graph is a measurement of the density when the state of the system was far from phase transition. So Shami excited an acoustic pulse. There was a change in density, but there was a dispersion, and by the time the pulse arrived the sensor, Shami couldn't measure any significant change. In contrast, when the state of the system was close to transition, then using the same amplitude of excitation, Shami got this significant change in density. So an increase followed by a decrease. And when I saw these measurements for the first time, I was really amazed, because for me this shape really resembles the shape of an action potential. Although, of course, we're talking about a density measurement and not an electric measurement. So I'm going to get to how these things are related in a couple of slides, or a few slides. And Shami can also measure the propagation velocity of acoustic pulses in membranes, and under different conditions, they range between 0.1 and 100 meters per second, which is the same order of magnitude as action potentials in different cells. Yes, and here's the mathematical calculation. So the lower dotted dashed line represents a density as a function of time when the state of the system is far from phase transition, and the solid line is a measurement using the same amplitude of excitation, not a measurement, a calculation, of course, when the state of the system is close to phase transition. And in order to explain these graphs, I have to show you the same pulses plotted in phase space. So the purple line is directly related to the dotted dashed line in the middle figure. So we have a starting point. It's this dot here. It's sufficiently far from phase transition. And now when we excite a pulse by locally injecting pressure, there's a local increase in density that's going to the left, and at the same time an increase in pressure that's going up, and at the same time increase in temperature that's going in the 3rd dimension, which you don't see in this projection. Then energy is transferred to neighboring molecules, and we get a decrease in density, pressure, and temperature until we recover back to the initial state. In contrast, when the state of the system, that's the green line here, and the starting point was here, when the state of the system was close to phase transition, now using the same amplitude of excitation, caused a significant increase in density that's going to the left, with almost no penalty in pressure. That's because of the shape of the phase diagram. Once the state of the system reached the condensed phase, suddenly it senses this exclusion of volume. So the density cannot increase anymore, but pressure rises up. So this line rises up to almost 20 times the critical pressure. Then pressure goes down, and subsequently density goes down until you get recovery. So this is a significant difference from the behavior of the pulses far from transition because of the state diagram. And from the equations, we can find, from the parameters of the equations, we can find proper scales. So we have a time scale and the velocity scale, which are directly related to the critical point of the phase transition, that's this point up there, and the viscosity of the material. So different materials will have the same pulses near phase transition, but with different scales. If you put in numbers of typical lipids, like DPPC or DMPC, you get scales of the time scale of the order of milliseconds to 10 milliseconds, and the velocity scale of the order of 100 meters per second. If you try to put numbers for water, for example, the time scale is picoseconds, right? So here's a plot of several density aspects as a function of the amplitude of excitation, and here's the parallel pressure aspect. At small amplitudes of excitation, these are the dotted and dashed lines here on the density, the pulses do not reach the condensed state, so there's hardly any change in pressure. You don't see any pressure signal. However, once this state of the system reaches the condensed state, the pressure increases significantly and is very sensitive to the amplitude of excitation. And we also have the parallel temperature aspect, which is adiabatic, so it increases and decreases. And what I wanted to show you in these three graphs is that the three aspects, these thermomechanical aspects, they start and end at the same time, but the shape of each aspect is different from one another. So this is not a linear theory, these are nonlinear pulses that are coupled to one another. And you can calculate the amplitude of the pulses as a function of the amplitude of excitation, and there is the sigmoidal response. So at small amplitudes of excitation, we are in the expanded phase, there's almost a linear increase. As we reach the phase transition region, we get this sharp increase in amplitude of the pulse, and as we reach the condensed phase, due to the exclusion of volume, there's a saturation in amplitude. And here's an experimental measurement by Shamil Shrivastava and Kevin Kant and Matthias Schneider, which qualitatively resembles these results. My results resemble them. They go first. Right, so these pulses were shown to experimentally annihilate, and I can just show you kind of a movie of the calculation. So this is the density field as a function of space, and we have these two acoustic pulses propagating toward one another. I'll just do a fast forward. As they get closer, they meet, and after collision, nothing comes out from the other side. And finally, it is natural from the equations to excite the system by different means. So instead of injecting pressure locally, I can inject temperature or energy. And you can see that we get very similar pulses by going on different dimensions. Again, because the system is nonlinear, the dynamics are governed very strongly by the phase diagram. So let me conclude this first part of a thermomechanical analysis. So I was focusing just on the classical acoustic aspects. So if you consider a soft material by conservation laws and a state diagram which represents the material, acoustic pulses simply emerge along with the following properties. So the time and velocity scales are related to the critical point and viscosity of the material. You have a sigmoidal response to excitation amplitude, annihilation upon collision, and they can be excited by different types of stimulations. But we all know that action potentials are measured electrically. So we have to include electricity somehow into this model. And electricity that not only lives on the membrane, but we have to think about the third dimension, about the bulk where electric fields will change. And indeed, you have electrical changes in lipids, because any soft material which is electrically charged, when you will have changes in density, it will change the charge density, and therefore it will induce local changes in electric fields. And these may be detected by distant electrodes. Here's an example of a measurement in a lipid monolayer. So what you see in red and black are two measurements of the local pressure as a function of time. And in between these two pressure sensors, Josef Griesbauer and Matthias, they used this local surface potential sensor, and they measured a change in the surface potential. And you can read the scale on the y-axis on the right-hand side is of the order of a few millivolts. Now, in this example, this is a small amplitude acoustic pulse. So it was in the expanded phase and the amplitude changed only a little bit. It didn't traverse into the other state. To the best of my knowledge, there is no measurement which actually measured the electrical change when the lipid changes to the other state back. But it gives some motivation that indeed when you have changes in density, you will have changes in electric charge, and now let's model that. So we go back to our two-dimensional surface represented by the 5 fields, density, pressure, temperature, etc. And we want to think about Maxwell laws of electrodynamics. So we want to incorporate these. So I'm going to focus on electric fields and electromagnetic fields. I'm going to neglect several things because, as Matthias said, I want to look at to see the forest for the trees. So I will, at the end of the talk, I will get a bit to things that we should extend here. Anyhow, so we had Gauss law and Ampere's law, which describe electricity, and these things are related to everything by the charge density. And the bulk is not empty. There can be mobile charged particles that move due to these electric forces. So we want to add these. We especially want to focus on protons because it is known that protons highly absorb into the interface. So we want to take protons and hydroxides. And we need to have some salts to get the physiological screening length. So the minimal ansatz we can use is one type of monovalent cation and one type of monovalent anion. So I have added these additional 5 fields. The electric potential field is phi and 4 concentration fields of these mobile particles. And the charge density of the interface is linearly proportional to the density of the material. But if particles adsorb into the system, it reduces the electric charge, the charge density. So I'm using Langmuir adsorption model, which has been used in different independent systems. And the dynamics of the particles in the bulk are described by the conservation of mass. So basically they can move because of random diffusion and due to electric fields. There's one more assumption here, is the question of what happened to these particles at the interface. And in principle, there should be permeability. However, permeability is known to be state dependent and there's not enough data on that. So for this model, I'm neglecting or ignoring any permeability. I will show you that still there will be an electric aspect which co-propagate with the acoustic pulse, but I will talk at the end how it is important to incorporate the permeability too. So anyhow, so we have our original hydrodynamic equations, and we added Maxwell laws of electromagnetism, Langmuir law, and Ernst Planck. These are all known equations, and we calculate them all together. So we get an electric potential field. The solution looks pretty much like this. This is a famous Poisson-Boltzmann solution. Basically, far away at infinity, the electric potential is 0, somewhere here. As we approach the membrane, the electric potential remains 0, because the particles screen the charge on the surface. Just at the screening length of the order of a nanometer, we start to feel a change in the electric potential, and as we approach the membrane, the electric potential is most negative, because the charge density is negative. Within the membrane, we assume that the electric fields are 0, and as we cross to the other side, the electric potential increases again until it reaches 0 after a nanometer or so. So you can clearly see that there is no electric potential difference here. And this is because the system is symmetric on both sides. If you break the symmetry, for example, by considering a different ionic content on both sides, or by assuming a different adsorption of particles to the interface, or even just by geometry, cylindrical or spherical geometry, when the system is broken, suddenly approaching the interface from both sides results in a different decrease in electric potential. So we get an electric potential difference. And that's it basically. So now we solve the equations again. So we have an acoustic pulse, and changes in density will cause changes in the concentration of particles near the membrane. Specifically, protons will change their density near the membrane. We will have a pH aspect. And the electric potential difference will change too. So here is a plot of 2 examples. In black, I considered an asymmetry in the adsorption of protons onto the membrane. And in blue-green, I considered an asymmetry in the ionic content of the salts. And there's a density and pressure aspects which look just the same as what I described previously. There's also a temperature aspect, I just didn't show it. but there's a parallel change in density of protons. So the pH at infinity is 7. And as you approach the membrane, the pH is still 7 all the way until you reach the screening length. So just a nanometer or so before you reach the membrane, suddenly protons accumulate near the membrane because of the negative electric charge of the surface. So you have a decrease in pH up to about 3.5. And when we have changes in density, we have changes in local density, and therefore the protons change their concentration, and some of them absorb or reabsorb, desorb from the surface. And there's also an electric potential pulse. And you can see how both the pH and the electric potential pulse resemble the shape of the density aspect. But it's important to stress that in these examples, the relation is not linear. So these are nonlinear pulses, and the dependent on density is nonlinear. But still, both pH and electric potential difference, they obey the same kind of sigmoidal response. And you can extract the scale of the voltage from these equations, and it is related to the critical temperature, so it is of the order of tens of millivolts. And let me just compare this electric aspect with action potential. So here's a calculation of a pulse from the Hodgkin-Huxley model. So it is a representation of an action potential in the squid giant axon. And here's a measurement of an action potential in a plant cell. And here's the calculation of the electrical aspect from this acoustic model. So you can recognize that the qualitative shape is not so different. So we can recognize a rising phase, a falling phase, and an undershoot phase. And I also have some examples where I played a bit with the parameters. I never published it, where I can also get an elongation here, a shoulder on this part, which kind of resembles a bit of action potentials in muscle cells, which look a bit different. And also the scales are of the same order, so both the time scale and the voltage scales, but of course the resting potential and the pulse amplitude are not identical to what we find in cells. And the reason is that there are still many details that are missed. So let me just go to these kind of missing details before I conclude. Right, so there are many things that I've neglected which are important. The hydrodynamics of the bulk. It's very easy now to extend it. You just need to add conservation laws at the bulk. And it was shown by Julian Kapler and Roland Metz that the hydrodynamic of the bulk is important to correctly get the velocity, the propagation velocity of these acoustic pulses, and to add dispersive terms. And if you want to model the thermal propagation of the action potential of the pulse across the bulk until you reach a thermal sensor, so if you want to replicate the measurements of Tasaki, you also need to incorporate kind of the thermal conductivity of the bulk. I've ignored magnetic fields, even though it is known that action potentials carry a magnetic change with them, and it is known that action potentials can be excited by magnetic fields, but it's very easy now to add it. I was focusing on a planar geometry and planar waves, but again, the equations, you can now change the geometry to get cylindrical or spherical shapes. You can think of waves that are not planar, circular, things like that. The phase diagram. Van der Waals, although qualitatively similar, is not an accurate description of what we get in lipids. And if you want to get the numbers correctly, like the amplitude of density, etc., then you need to get a more accurate model of that. An important point is that all of the constants I've used in the model are known experimentally to be state dependent. So viscosity, heat capacity, thermal conductivity, adsorption of particles to the membrane, and the permeability across the membrane are all known to be state dependent and are all known to change most significantly at the interface. There are even some examples of ionic selectivity in experiments. So we somehow need to get more accurate data, so I will not make up equations or fit them, but we will have some kind of accurate state-dependent description. And this is where kind of also the molecular aspect makes a difference. So different ionic content, different protein content in the membrane can make a difference in all of these parameters and others, like elasticity. And I want to give one last example, which I have ignored, and I think it is of relevance. I've considered the two leaflets of the membrane to be at the same state, so same pressure and same density on both sides of the membrane. There is this one paper, I just plotted it here, this one picture, where they use this kind of simplified model, but they consider two different in the bilayer, the two different leaflets may exist in different states. And they show how it results in this kind of oscillation of electric potential. And to me, it really resembles a train of pulses, which is such a typical measurement in action potential. So again, I think this is something else which is important. So let me just conclude. I've started from classical physical principles, which must exist in the soft material, and I showed you how acoustic pulses are something which must emerge along with the different aspects, including pH and electric potential difference. These are the things that Thomas and Matthias were talking before. And there are two implications I would like to point out. One is that this macroscopic description, which does not go into the molecular details, may be of relevance for biology. And the other one is that the computational scheme, which is often used in computational neuroscience, may be more complicated than simply this all or none or 0 or 1 way of thinking. So cells are not just fired or didn't fire. The state diagram, when the cells exist in different states, they respond differently to different excitations. And specifically, I showed you that some of the aspects of the pulse, for example, the pressure and the temperature aspects, do not obey the sigmoidal response. So when you have measurement of a sigmoidal response with your electrode, you're not sensitive to other aspects that may respond differently. And with this, I would like to thank the many people who have influenced this work, and thank you for listening.
Thanks a lot, Matan, for this nice presentation and staying in time. We have questions. We start back there, all the way up there, and then go down.
For the talk, I like your model very much. It's a fascinating model. There's one thing that I'm not very sure, maybe my understanding is wrong. It's regarding when you excite your system with a pressure pulse, and the exciting pulse is hundreds bigger than the pressure occurring at phase change. And I just wonder if you could give more explanation on this and how this could happen in real natural action potentials, if action potential is an acoustic pulse.
So, first of all, just to defend this, these are the equations, and for the given parameters, these are the excitations that I need to use in order to get. Now the question is it has any relation to reality? And my answer is that I'm not exactly sure. So I was asking the experimentalist, can you estimate, when you excite mechanically, can you estimate the amplitude of excitation? And we're not exactly sure on that, but it's an important question. Another thing is, how exactly the excitation occurs? When you excite, is it only mechanically, or does it also add some heat? When you shine light, do you add only energy or also heat? So these are small things that you're absolutely right. We need to be more accurate about that, but I have no idea if when you excite things mechanically, when Shami does it mechanically, I'm not sure what are the amplitudes used as compared to the critical pressure.
Shami, then you show, yeah.
When the collision happens, can you track what is happening to the energy of the pulses? Is it going high frequencies or something, or
yes, absolutely. I mean, when you have the solution, you have the complete energy field, so we can look at that. I would like to say in that regard that for these particular parameters, I've used pulses annihilate, but I had some time when I played a little bit with the parameters. That was before I was sure what are the parameters of lipids. That was before I actually talked with Matthias and Kevin. Anyhow, for different regions of the parameter space, you can get many interesting behaviors of how the pulses behave when they go toward one another. So in some cases, there can be some parts that actually go through. In other cases, the pulses slow down and actually stop before they meet one another, although they remain stable. So I'm not sure if these regions of parameter space are physical, but I mean, I think the beauty about hydrodynamics and Maxwell's electromagnetism is that the theories are based on very simple and well-founded laws, but they are extremely rich. And when you combine the two, I mean, it's no surprise that biology is so rich.
Sophia?
Two questions. One theoretical and one practical. Theoretical. Now you talk about idealized material near phase transition. So a magnet is something like that. A magnet.
Magnets, you mean the
Yes.
phase transition
And
of
you
magnets?
can describe the state of the spin in the magnet by the Ising model, and you can have an actually outstanding description of the phase transition of a magnet, which many physicists have been spending their grey matter.
So you mean instead of a van der Waals, to replace it with an Ising model or this social?
Just to have an idealized system to work with. So my question is, under this condition, would you find exactly the same thing? And in addition, you would have a good theoretical solution for your pulse.
I would say that I'm not sure about Ising model, because I'm not sure how in Ising model, I mean, what I need is a relation between pressure, density, and temperature as a starting point. Although I didn't show you all the details, but there's also an aspect added by Troible of a relation to pH, and so you need to have an equation which describes the behavior of the state diagram. So if you know this, if you know how pressure responds to density, if you write an equation, or if you just make an approximation, the way Thomas Heimburg or Julian Kapper did it in their works, they just took an approximation of some part, it will work. It will work the same. It's not surprising that what I get and what Thomas gets are not so different from one another, because as long as
This means that it's would be some kind of universal way of having some propagation of signals in a solid state.
I don't see why not, but again, I cannot,
So why not?
I don't know, I don't see why not, but since I don't want to promise things which I cannot stand behind them, I would say, okay, we need to maybe discuss more detailed examples, and then
Okay,
probably
now
you
this
can
is
find
maybe some interesting. Now, considering the similarity of the acoustic pulse and the Hodgkin and Huxley model, you have an undershoot in the Hodgkin and Huxley model, which is usually assigned to potassium, essentially the first phase being assigned to sodium. I don't see why you should find this kind of thing with acoustic pulse.
Okay, so I have 2 points on that, and again,
So
there's no way I can
it's
answer
a
you.
pure coincidence,
Yeah,
or an artifact, or whatever you.
So I have 2 points on that. First, when you measure action potentials in the plant cell, I showed you this example of the plant cell. The figure on the right hand side.
Yes.
The molecular description of action potential in this plant cell is that calcium goes in, then chloride goes out. This is what causes the depolarization. And then potassium goes out. This is what causes the repolarization. However, in these plant cells, you don't find this hyperpolarization region. So there is potassium leaking out, but you don't have repolarization. Hyperpolarization.
So why do you find it with the acoustic pulse?
Okay, the second answer is that in regard to acoustic pulses in general, the shapes of many acoustic pulses is this one. So Conrad knew about it in 1999. He was referring to this hydrodynamic book from the 1800s. So you get this increase in density, and subsequently they call it a rarefication, a decrease in density below the resting density. This is a very common behavior in acoustic pulses. Pulses increase in density and then decrease before they go back. So there is no fine-tuning in the model. There is no single fit parameter. These things simply emerge as they are. If you go to solitones, I think you don't get that for the solitones, but yeah, for this one.
Connie?
Yes. I would like to answer to your question. The thermodynamics is first. Phase transition is inferior, but I don't discuss now phase transition and the troubles there. I discuss precisely what we call potassium after hyperpolarization. It is Horace Lamb from 1860 something. Hydrodynamics was a Bible. And there I discovered that he had, just on plain hydrodynamics, classical, in 1 dimension, 2 dimensions, 3 dimensions. And he has one picture with the 3 figures. And he interestingly started with a Lorentz shape, pressure, thing on a one-dimensional, and point-like in a two-dimensional, and point-like in a three-dimensional. That's how I first saw it must be this way. And in the one-dimensional thing, it's exactly as an excitation, a symmetric Lorentz shape in this case. In the three-dimensional, where the point doesn't matter, it's exactly anti-symmetric, the pulse which occurs. It's a non-volume thing. And in the two-dimensional, it has this shape with the afterwave. And if you look in detail, the afterwave comes from the fact that you have this conservation of matter, you should say. And in one dimension, it just has to be conserved. In three dimensions, it's zero respect to volumes. And in two dimensions, there is just like in the front of a ship, of a boat, the wave, it will always have an afterwave and sometimes can have two afterwave. This was the key point I saw. It must be hydrodynamic, the thing. Now the key question is, how do Hodgkin-Huxley come to put it in a potassium picture, and how does this picture become so successful that we now put the potassium picture first and ask how can ever my answer is Hodgkin's answer. In 1964, the Nobel Prize in his book Conduction, page 75, something, when asking about the physical basis. And he's even more clear in 1975 in physiological.
Connie,
Yes.
you're not holding a talk, okay? Just keep it.
No. I say that Hodgkin's answer to your question about potassium is that it was Huxley who invented the mathematical picture, and one is asking for the physical basis. And I think it's better than to give you my extended version. It is Hodgkin in person, in things he wrote alone.
Well, I've got one point,
Yeah.
which is, thank you very much, is that due to this potassium story, whether you like it or not, there is a refractory period.
That's it.
Do you see any refractory period for the
Yes, absolutely. When the state of the system is in the condensed phase, you cannot excite the pulse again because it's already in the condensed phase. When it goes back, and actually the dynamics to go back into this rarefication phase, this undershoot phase, are rather quick, then suddenly you need a higher, an increase in amplitude if you want to send it back again. So you can see both there's this kind of absolute refractory period and partial refractory period. And you can recognize both just from the phase diagram. Thank you.
Thanks a lot.